Welcome to the deep dive. You've seen them. I mean, you've probably used them yourself, right? ChatGPT, Daily, Mid-Journey.
Oh, yeah, definitely.
These generative AI systems are just incredible. They can create totally new text, images, even code just from a simple prompt.
Mm-hmm. They've really changed the game in how we interact with tech.
So today, we're doing a deep dive into what's called the generative AI value chain. We're going to kind of pull back the curtain and look at the whole journey.
From start to finish.
Exactly. How these things get built, from the raw data they munch on all the way to the polished stuff we see.
And our goal here is really to give you a solid understanding, kind of strip away the jargon.
Yeah, get to the core of what makes these systems tick. We've got some great source material to draw on for this.
It's really about understanding the basic mechanics first. So generative AI, what is it? It's a type of AI that actually creates new content.
Right. It's not just fetching information that's already out there.
Exactly. It's generating something novel, something fresh based on whatever you ask it.
Okay, so high level then. How does it actually do that?
Well, during training, it basically digests just a massive, massive amount of data.
Like petabytes.
All
We're
right.
talking huge scale.
Oh, enormous.
Yeah.
Petabytes of internet text, maybe millions, billions of images. And it absorbs all that to learn the sort of underlying rules, the patterns.
The structure of whatever it's supposed to create, like language or images.
Precisely. And once it's got those patterns down, it can then sort of riff on them, recreate them with calculated variations to make something new.
So when you use ChatGPT for text, or maybe Delio or Midjourney for pictures, you're tapping into that whole generative process.
That's it.
Okay, so to really get how this creation works, we need the building blocks. And at the heart of it all, there's the model.
The model, yeah. Think of it as the AI's knowledge. It's basically a complex mathematical representation of all those patterns it learned.
And the way that knowledge is organized,
Yeah.
that's the architecture.
Exactly. The architecture is the blueprint. It's the theoretical design, how the model's parameters, its internal knobs and dials, if you will, are structured to process information and, generate the output.
Okay, and the story of these architectures, it's actually seen some pretty big leaps.
Oh, absolutely. If you go back, say, before 2014, the early days, we mostly had these things called probabilistic methods.
Right, simpler algorithms, good for stuff like autocomplete on your phone.
Yeah, exactly like that. Predicting the next word based only on the few right before it.
But they had limits.
Big limits. They couldn't really grasp long-range context, understanding a whole sentence or paragraph. That was tough for them. A real bottleneck for complex tasks.
So that's where neural networks came in, around 2014 to 2017.
Deep learning neural networks. And what's cool is they were kind of inspired by how neurons connect in, a real brain.
And they were better at meaning.
Much better. They could capture richer semantic meanings, understand context from surrounding words. That was a huge step for things like machine translation, a deeper understanding of language.
But still, not perfect.
No, they could still be slow, computationally heavy, especially when trying to understand nuances across like a whole document. Scaling them up was still a challenge.
Which brings us to the big one, the transformer architecture. 2017, Google Brain.
That was the game changer, truly revolutionary. And the key insight, the big innovation was self-attention.
Self-attention. Okay, what does that actually let the model do?
It fundamentally changed information processing. Instead of just looking at adjacent words, self-attention lets the model weigh the importance of all other words in the input simultaneously when interpreting any single word.
Regardless of how far apart they are in the text.
Exactly. So words way back at the beginning of a paragraph can directly influence how a word near the end is understood. This massively improved understanding complex relationships across long texts.
And it wasn't just about understanding better, it was faster too.
Much faster and more efficient to train. It really shifted the bottleneck away from pure computation towards, getting enough data and training cost effectively. It opened the door for models like Google's T5 and, everything that followed.
Okay, so models the brain, architecture is a blueprint.
Yeah.
Then the fuel is the training data.
Yep. And we're talking vast amounts, usually measured in tokens.
Tokens being like chunks of text, words or parts of words.
Basically, yeah, discrete units. And the scale. Well, GPT-3, for example, it was trained on something like 500 billion tokens.
Wow. That's, 300 billion words?
Yeah.
Where does all that come from?
All over. Common Crawl, which is just petabytes of scraped web data, digitized books from the internet, Wikipedia, Massive, diverse sources.
Now, there's something interesting our sources point out, this data paradox.
Right. So historically, making models bigger, more parameters was the main way to get better performance.
So we're seeing diminishing returns on just size now.
Exactly. The focus is shifting. It seems like high-quality data is becoming the really scarce resource, maybe even more than the capital needed to build huge models.
So it's not just more data, but better data. Cleaner, more relevant.
Precisely. Even for specialized things like training models on software code. The sources say the amount of available high-quality code data is woefully tiny compared to what they could use. Quality over sheer quantity is becoming key.
And this whole data thing runs smack into copyright.
Oh, yeah, that's a huge legal question mark right now. It's pretty clear that copyrighted stuff inevitably ends up in these giant training data sets.
So what's the thinking? Fair use.
There's a lot of speculation around the fair use doctrine, but it's legally uncertain. Lawsuits are popping up.
And companies are handling it differently.
Seems like it. Some, like OpenAI, tend to be less transparent about exactly what's in their training data, maybe to avoid liability. Others, like Stability AI with Stable Diffusion, were open about using the LAION database.
And then they got sued by Getty Images.
Right, because LAION apparently contained lots of proprietary images. So yeah, transparency has its own risks in this environment. It's a really complex legal mess.
Okay, so we have the model, architecture, data. Now the actual crafting process, pre-training and fine-tuning. Let's start with pre-training.
Pre-training is that first big phase. It's like the model's general education, K through 12, maybe?
Learning the basics.
Exactly. For a language model, this means absorbing that huge unlabeled corpus of text, the whole internet, essentially to learn the fundamentals. Grammar, facts, how language generally works. It's mostly unsupervised learning. The model teaches itself the foundations.
Okay, learns the basics, then comes fine-tuning.
Yep. After pre-training, you fine-tune. You take that generally knowledgeable model and you adapt it, specialize it, using more specific, often labeled data for a particular task or domain.
So that's how you handle domain shifts, like taking a general chatbot and making it good at medical advice.
Exactly. The general model knows language, but fine-tuning on medical texts gives it that specific expert knowledge.
And this costs money, presumably.
Oh, yes. The costs can vary wildly. Our sources give examples like fine-tuning a 6.7 billion parameter model with around 10 million tokens might cost under $40 and take a couple of hours.
Okay, manageable.
But fine-tuning with, say, a trillion tokens, that could be $200,000 and take maybe 10 days. So it scales up significantly.
And fine-tuning often involves supervised learning, meaning humans are in the loop.
Often, yes. Humans labeling data, humans evaluating outputs. This brings us to a couple of really key developments. Instruction tuning and RLHF.
RLHF, reinforcement learning from human feedback.
Right. Let's take instruction tuning first. This basically teaches the model to follow explicit commands. Summarize this text, translate this sentence, write a poem about.
And that allows for zero-shot generalization.
Exactly. The model can do a task it wasn't explicitly trained on with examples just by understanding the instruction. Like summarizing news, even if it never saw a news summary example during fine-tuning, it learns to follow orders.
Super useful. And RLHF, that's about alignment.
Yeah, human alignment, making the models more helpful, honest, and harmless. This is where humans come in and rank different outputs from the AI.
Saying this answer is better than that one.
Precisely. That feedback is used to build a reward model, which then further trains the main AI to produce outputs that humans prefer.
And OpenAI used contractors in places like Kenya, Uganda, India for this.
They did, yeah. It's a very labor-intensive process, getting all that human preference data, but it's crucial for making the model safer and more useful in practice.
And there's one more technique mentioned, chain of thought prompting.
Ah, yes, so that's more of a frontier technique, really interesting. It's about improving the model's reasoning, especially for things like math problems, common sense questions, symbolic stuff.
How does it work?
You basically prompt the model to think step by step, to show its reasoning process before giving the final answer, like showing your work in math class.
And that helps it get the right answer more often.
Seems to, yeah.
Wow.
Eliciting those reasoning steps makes it more reliable for tasks that require, well, actual reasoning on the fly.
Okay, so we've built and trained these incredibly complex models. Now, what's the cost of actually using them day to day? This is inference, right?
Inference, exactly. That's the stage where the trained model is put to work, making predictions or generating content on new, unseen data. your actual prompts.
And this isn't like a simple web search.
Not at all. Search engines retrieve existing stuff. LLMs generate new stuff, token by token. That's way more computationally intensive.
And the costs really add up. I saw one estimate, nearly 1 cent for a single 30-word ChatGPT response for OpenAI.
Yeah, the operational costs are pretty staggering. Supporting, say, 1 million daily users might need over 30,000 high-end NVIDIA A100 GPUs.
Just the GPUs could cost, what, close to $100 billion in capital?
Potentially, yeah. And then the day-to-day running costs, maybe over $100,000 a day just for compute, plus another $50,000 daily for electricity.
Wow. I saw another estimate putting OpenAI's daily tab for ChatGPT at maybe $700,000.
These numbers are estimates, of course, but they point to the same thing. Running these models at scale requires immense infrastructure and cash.
And the engines driving this are GPUs,
Yeah.
graphics processing units.
Yep, specialized chips. NVIDIA is the big player here, AMD too. Their highly parallel structure is just perfect for the kind of math AI needs. Lots of calculations happening at once.
And performance is measured in FLOPS.
Floating point operations per second. It's a measure of computational horsepower. Like NVIDIA's newer H100 chip boasts 67 teraflop PS, while the older A100 is around 19.5 TFLOPS.
So newer is always better.
Not necessarily from a cost perspective. The crucial metric is really FLOPS per dollar. And interestingly, in 2023, the source notes that the older A100 was actually more cost-effective per FLOP than the newer H100 just because of how they were priced at the time.
So it's not just raw power is bang for your buck.
Exactly. And GPU costs themselves bounce around like crazy.
Okay.
Macroeconomics, demand surges from crypto mining, or now AI, supply chain hiccups,
Yeah.
it all impacts the price.
And then there's the electricity bill. You mentioned $50 a day just for power for ChatGPT users.
Yeah, the energy consumption is massive. Google training its Palm model apparently used 3.4 gigawatt hours over 2 weeks.
Which is like powering 300 U.S. homes for a year.
Something like that. It's a significant energy footprint.
Are things getting more efficient at least?
Thankfully, yes. There are steady improvements in efficiency for inference. Newer hardware like that H100 chip promises big speedups and lower costs per inference, which is vital if these things are going to become more widespread.
Okay, and all this hardware lives in data centers.
Right, the physical home for all the servers and GPUs. And companies face a big choice. Build their own private data centers or rent capacity from cloud providers like AWS, Google Cloud, Azure.
Build versus rent. What's the calculus there?
Cloud is great for flexibility, getting started quickly, finding product market fit. But with the sheer scale of AI training now, especially for foundational models, building your own data center can actually be more cost-effective long-term.
Especially if you need tons of GPUs and can keep them busy.
Exactly. High utilization makes owning more economical, particularly with GPU prices being what they are. The scale of AI is kind of tipping the balance back towards private infrastructure for the big players.
Okay, last piece of the puzzle, but maybe the most critical for actual deployment. Guardrails and content policy.
Absolutely essential. This is the final step, basically putting safety controls on the model to make sure it doesn't generate harmful, biased, or just plain undesirable content.
And we learned why this is needed the hard way, didn't we? Microsoft's Tay chatbot.
Oh, Tay, 2016, a classic cautionary tale. Microsoft released it on Twitter, designed to learn from interactions.
And within hours it was.
Well, awful.
Yes, spewing racist, genocidal stuff it learned from trolls. They had to pull it offline in just 16 hours. A stark lesson about uncontrolled AI learning.
So how do modern systems like ChatGPT compare?
Much, much better. They have what our sources call robust guardrails. They're great examples. ChatGPT refusing to list positive things about Nazis.
Or add an important context about forced labor when asked about German highways built during that era. Right. It shows a much more sophisticated approach to preventing problematic output.
How do these guardrails actually work? Are they checking prompts or outputs?
Can be both, or even within the model itself. Checking the user's input before generating saves resources. Checking the output after generation allows for more complex reasoning about whether the response is appropriate. Or you can build safety constraints right into the model during fine-tuning. Often it's a combination.
And the result is that current chatbots are pretty good at deflecting tricky stuff.
Very effective generally. They'll refuse to help with illegal things. How do I build a bomb? Nope. They usually avoid taking sides on contentious political questions. Is X better than Y? They'll demur.
And sensitive moral debates, too.
Yeah, like questions about abortion or other deeply personal ethical issues. They're typically programmed to remain neutral or decline to answer directly. It's a core part of responsible deployment.
Wow. Okay, so we've really walked through the whole chain today,
Yeah.
from the core architecture
Yeah, the models, the
Yeah.
transformers.
to the massive data needs, the pre-training, the fine-tuning with human feedback,
The huge costs of inference, the GPUs, the electricity.
and finally those critical guardrails for safety and ethical considerations.
It's an incredibly complex ecosystem, isn't it? So much rapid innovation, but also huge challenges around resources, cost, and just using these things responsibly.
Absolutely. It leaves you wondering, as this tech keeps evolving so fast, what's the balance going to be? This relentless push for bigger, more capable models versus the spiraling costs, the energy demands, the ethical tightropes.
It's a fundamental tension in the field right now.
So, a final thought for you listening. As generative AI continues this trajectory, where do you see that balance point? What stands out to you most about how these incredibly powerful tools are evolving and how we're learning to manage them?